Excellent. Okay. Good morning, everyone. Welcome to Superconductivity Lecture 4. A particular welcome to those who are new in the audience. I see there are some, which is great. Before we start, many of you will already have had the notice that Peter Fulda, the founding director of this institute, died yesterday. For those who didn't know, I'm sorry to break it to you at the beginning of a lecture, but it would seem quite inappropriate in a lecture on superconductivity in his institute not to say a word of tribute at the beginning. Obviously, there are many, many people in this institute and some in this audience who knew Peter much better than I did. He was basically a nice chap with whom I used to talk at lunch when I was visiting PKS. And I have fond memories of really remarkable stories of the 1950s and 1960s that I heard from him, including crossing from East Berlin to West Berlin a few years before the wall went up by hiding luggage in a different carriage of the tram, because if the guards saw you with luggage, they'd figure out you were trying to move and move you back. Apparently there were several attempts at this before he finally made it. So he lived through some times, but he also created some times, which I think is I think he clearly was pleased, actually, at what he'd achieved in PKS. So I thought I'd say a word at the beginning. Clearly, his interests intersect with some of the stuff we'll be discussing here. I have no idea whether we will get as far as the Fulda-Ferrell-Larkinov-Chinnikov phase of superconductors, but we will certainly, of course, make sure we say something about it. Good. With that RIP, let's crack on. I continue to bring you here under false pretenses because this is Superconductivity Lecture 4 and we're not at superconductivity yet.
We're going to extend this course, Chris.
Well, look, we'll do what we can. But there are a couple of crucial things that I need to talk about still in the regime of superfluids. We might get both of those done today, but obviously please don't let that stop you from asking questions. If we need more time, we'll book more time. It's important that people keep understanding what's going on. So far, what have we done? We've looked at the phenomenology of superfluidity. We've noted that in its two-fluid nature, it looks a bit like Bose-Einstein condensation, and it seems to be mainly bosons that do it. But then we argued that a Bose-Einstein condensate, i.e. a non-interacting gas of bosons, shows condensation but actually doesn't show superfluidity because the dispersion relation for the excitations out of the superfluid is quadratic, and therefore, by Landau's argument, the critical velocity of the superfluid would be zero, i.e. there is no superfluid at all. We then wrote down a theory of interacting bosons, the weakly interacting Bose gas. We demonstrated that if I take a coherent state ansatz for the ground state of that problem, then as a result, the excitations out of that become linearly dispersing, and that allows superfluidity up to a finite critical velocity as per Landau's argument. And that's where we finished on Wednesday. So what I'd like to do now is to just highlight a couple of things that we can predict fairly easily from this coherent state ansatz. And really that's just a couple of practical problems of superfluids with particular boundary conditions. So I want to think about a superfluid with a wall, right? So what happens to the superfluid order parameter as I move towards the boundary of the system? And then I want to think about what happens if I put a superfluid in a rotating bucket. And that will introduce us to the idea of vortices and irrotational flow and so on. Good. So,
Chris, can I ask you, at what point were you will be closing the loop, presumably, on showing how the coherent state ansatz has ended up accounting for the strange behavior of the power laws of the heat capacity and other things that you talked about in the phenomenology?
Well, okay, so some stuff it's already managed, right? So the fact that the dispersion relation of the excitations went from quadratic to linear automatically means that the heat capacity will go from T to the 3/2 to T cubed. point.
Yeah.
So the heat capacity is already there, and I flagged up at the time that that looked like it would be a signature of a linearly dispersing number non-conserved boson, and we now know that those are the Bogoliubov sound-like excitations above the superfluid.
Yeah.
So that one we've done. I wasn't actually planning to go back and try and recalculate the t to the fourth, but we certainly can.
It would be interesting to know, I mean, rather than you necessarily recalculating it, if we knew whether or not the coherent state got the t to the fourth.
Yeah, whether it's now working, and I would have to check that myself.
Yeah, okay.
Okay, so let me note that as a question that I will definitely at least check the answer to, and then if people want to see more details on how it works, I can show them when I know myself.
Very good, okay.
Good. Anything else before we get going? Splendid. So, what I would like to do now is to make a bit of an extension of the theory we've been writing down so far. What we wrote down before was a Hamiltonian, and we talked about the ground state, and we talked about low-lying excitations above the ground state. But it's also good to be able to talk about what happens as you heat the superfluid, close to the lambda point, so where it also goes normal. That requires work beyond a Hamiltonian. You can't do that description using just low-energy excitations. So I'd like to write down an extension of the coherent state ansatz, if you like, to the case of finite temperatures. So, to deal with phenomena near Tc, we need an ansatz based on the coherent state idea. And this is the so-called Ginzburg-Landau theory, which basically says that even without knowing the microscopic origins of the Hamiltonian I wrote down before, I could have reasoned what form it must have just by knowing that there is a complex order parameter and by asking which real quantities can I make from that complex order parameter to be contributions to the energy. Okay. So we will assume a complex order parameter psi of r, and obviously we have in mind that this is just analogous to the order parameter we got at 0 temperature, except now it will be a thermal expectation value of the annihilation operator, not a ground state expectation value. And now the question is, imagine that I have a sample of superfluid at some temperature T. That means I should think about its free energy, not its energy. What possible form could its free energy take as a functional of the profile of this complex order parameter? So clearly there could be a constant. We're not usually interested in the constant because it's derivatives of the free energy that give us all of the physical observables, but in principle there is some constant here. And then since the free energy is a number and this is a function, we must clearly integrate over all space. And the question is, what do we integrate? So the lowest power of this that is real and analytic, which is an assumption we're sneaking in, is the square modulus of this complex number. So that suggests that I should probably have a term here that looks like a over 2 square modulus of psi. You might wonder about why the half. It's just so that when I differentiate that will cancel off, right? It's just for convenience in the equations of motion. And then the next thing I can write that's real is the square of that. So that gives me b over 4 psi to the 4th. And in principle, there are higher terms, but we'll see that at least near the critical temperature, we don't actually need those higher terms to describe the physics. There are deeper arguments based on renormalization and so on, why those higher terms can be dropped, but let's just say for the moment that we're dropping them because we don't need them. We also know from the zero temperature expression for the energy that this order parameter resists being varied in space. So there was an energy penalty at zero energy for varying the order parameter spatially. Presumably that survives at non-zero temperature. So we should also have some term that punishes us for spatial variations. And again, in order to make that real, I have to make it the square modulus of the gradient. I've written the prefactor as if it were just the regular kinetic energy that we had from the weakly interacting Bose gas, but actually you can always write the prefactor this way if you don't commit to the value of m star. So that's not really a restriction, it's just to write this prefactor in a familiar form. In principle, this symmetry reasoning doesn't tell you what any of the prefactors of the terms are, but there are general things we can say about how the theory will behave that don't depend much on what those prefactors are. Okay, so this is not derived. It's inspired by what we saw at zero temperature, but presumably, unless something disjunctive changes when we heat the superfluid, the finite temperature theory must look something like this.
Could I ask a historical question? Because this type of reasoning, of course, is this, it's a horrible theory in the sense that it all looks so simple, yet it's extremely deep, and it is, making this link between thermodynamics and quantum mechanics. Were they the first to do this? When did this understanding of the way that you combined quantum and thermodynamics really originate?
I don't know of anything before this theory. Yeah, I mean,
it's another one of these bloody Landau things.
It is, yeah. Yeah, and it was definitely inspired. So they knew about Bose-Einstein condensation, and so they knew about the condensate having a macroscopic wave function. And so in the early literature, people talk about this as a macroscopic wave function. I've deliberately not presented it that way because I don't think it's really a good description of what this complex order parameter is. It's a coherent state eigenvalue. It just happens also to be a complex number that depends on position. So from that point of view, it looks like a wave function. Yeah.
But London had really pushed the wave function ideas, right?
Yes.
Superconductivity.
That wasn't originated by Landau.
Okay.
Paul.
To be a little bit pedantic, in principle, we could also have other derivative terms, right?
Yeah, that's correct. So
are they also irrelevant, like Archie irrelevant, or why do we drop them?
So do you mean sort of higher derivative terms?
We could have higher derivative terms, or we could also have higher powers of exactly this term.
Yeah, indeed. Which effectively would be a.
True.
Would be a higher derivative term. Yeah, again, the rationale is that if we're interested in long wavelength physics, we hope that we won't need too many powers of the derivative. So if I Fourier transform this would be q squared, the higher terms would be q to the 4th, hopefully at small q they're less important. But really the only way to check is to do the first few, see what you get, add further ones and check that nothing changes. So, yeah. So, it turns out that for the physics I want to show, and for basically all long wavelength physics in these superfluids, I don't need more than that leading derivative term, but that's not obvious at this point. one has to add higher terms and check in some way that they don't make any difference.
Just one question. Can this functional be derived in any way?
I mean, in some cases, yes. So if I have an integral model, which I can kind of solve exactly quantum mechanically, which shows superfluidity, then I can, at least in principle, exactly write this down by just taking the thermal expectation value of the internal energy and the entropy in terms of the operators, and then those will get turned into the field. In most cases, though, we don't have the ability to solve the actual Hamiltonian model except at low energies. So in most cases, we can't follow the predictions of the model up to the critical temperature. And so in those cases, this is a well-motivated ansatz rather than something we can prove.
But, as is half knowledge here, didn't Gorkov do this famous work reconciling BCS and Ginsburg-Landau, where he must have done something like telling us?
Yes, but really that was a low energy calculation. It didn't prove that it would work right up to TC. And I mean, you can see that I've somehow assumed in these few terms, or it looks like I've assumed that the order parameter is quite small, because I've truncated this expansion. On the face of it, that should be a good assumption near the critical temperature, and it should get worse as you lower the temperature because the order parameter will grow. And as the order parameter grows, you might start worrying that these higher terms are going to become at least quantitatively important. And they do, right? So I can't go to low temperatures using just this term. So what Gorkov established was that there is an expansion of this sort for the free energy at low temperatures. And then you argue, well, the temperature only appears in the parameters, so the expansion must work at any temperature. But the expansion with the truncation is really only a good idea near TC.
Well, I do think this is psi can actually be defined from microscopic quantities, so so it's not just something made up, no. So you can really write it down as like an expectation or related to some expectation values of bosonic operators, no.
Yeah, no, I agree with that. Yes. Yeah. Yeah. Well, I mean, we'll talk more about how that works also in the superconducting case. Mm-hmm. Yeah, I mean, you can, but you don't know that the free energy takes this form in terms of psi unless you can get it out of a calculation, and typically you can't do that calculation in a controlled way near TC.
Yeah, so I guess the assumption is that, like, okay, psi you can actually write down, but then the free energy of your model is kind of similar to this free energy. That's the assumption.
Yes, exactly. But that's based on continuity from low but non-zero temperatures. It seems pretty plausible.
But yeah, I just think like often the psi is introduced as something completely made up, but you can...
Oh, no, don't worry. We've talked extensively about what the origin of the psi is. We've written down a coherent state ansatz. We have nailed the question, I think, of what this psi means and what the condensate phase is.
Okay, I'll shut up.
Good. Okay, so let's ask what this means. Of course, one of the things that might worry you is that the temperature is not explicitly present anywhere here in this expression. And yet we'd like to find the critical temperature, and we'd like to ask how things depend on temperature near the critical temperature. So somehow we have to figure out how these parameters depend on temperature, at least. Otherwise we're not going to do very much, not going to be able to do very much with the theory. Okay. So the first question to ask is, how do A, B, and M star depend on temperature, and potentially on other control parameters in the experiment, but temperature's the obvious one. So the first observation is that the minimum free energy is always achieved by setting spatial gradients to 0. And here is a crucial caveat, provided boundary conditions allow. So in the problem where we have a superconductor with a boundary, it will not be possible to set those gradient terms to 0 because they describe the development of superfluidity as you move away from the boundary. But if it is possible to set the gradients to 0, that will always lower your free energy. The second observation then, well, from that first observation it follows that if we can do that, this becomes a function, not a functional. This integral just becomes the volume of the system. This term is gone, and then we have just a over 2 square modulus of a constant plus b over 4 square modulus of a constant, dropping the higher terms, as we always do. And now minimizing the free energy is kind of easy, because we just have to pick the mod psi that makes this the smallest. And the crucial observation is that the form of this function depends on the sign of A. So if A is positive and B is positive, we always have to take B as positive, otherwise there wouldn't be a minimum at all, right? If this free energy has a negative quartic term, then you can make it as negative as you like, and that's unphysical. So if B were negative, then we couldn't have truncated the expansion here in the first place. So our truncation is based on the idea that B is positive. And then if A is positive and B is positive, our free energy just looks like this, and the minimum is obviously at the origin, i.e. the complex order parameter vanishes in the case where A is positive, and so that must be the normal state. Whereas on the other hand, if B is positive but A is negative, I've ignored the constant term, because obviously that doesn't really matter for any of this. So if A is negative, then we get the minus quadratic bit winning first, but then the quartic bit taking over. And clearly what happens here is that the minimum is achieved at some non-zero value of the order parameter. And so in this case, mod psi is not equal to 0, and so this must be the superfluid phase. So just by looking at the form of that free energy expression, we can work out that the transition from the normal state to the superfluid must happen when the coefficient A changes sign. So the normal to superfluid transition happens when A goes negative, and that motivates an approximate form for A, which is that it is proportional to T minus Tc. This obviously has the property that if the temperature is above the critical temperature, A is positive, and then our equilibrium value of the order parameter will be 0. If T is below the critical temperature, our A will be negative, and then there will be a non-zero value of the order parameter. Yeah.
Is there any justification for it to be linear in T other than it just being, that's the simplest thing I can think of?
The argument is basically that if we assume that it is a differentiable function of temperature, then this is just the first term in the Taylor expansion around Tc. Right? The argument is that for the parameters of the free energy functional, there's no reason for them to do anything weird at Tc. So you'd expect them to be regular differentiable functions of temperature, and so then I just look for where A is 0, and around that point, functions that are 0 are generically linear around the point where they're 0, unless there's a symmetry reason why they shouldn't be. So I think it's kind of, it seems a sensible thing to assume there's no reason to write any other power, and so there's no reason why this linear term in the Taylor expansion shouldn't exist. So we assume it's the one we should keep. Okay. So that actually lets us make a prediction about the critical exponent, because so we can ask, how does the modulus of the order parameter depend on temperature when we're just below Tc? Obviously just above Tc it's exactly 0, but you can see that as I make this A parameter more negative, I'm going to go through a sequence of curves. So the minimum is moving outwards. Right? You can see just from this graph that the order parameter is strengthening as A becomes more negative. And so this tells me that the equilibrium order parameter should grow as the temperature is lowered. And we can say how, because if f minus f naught is a over 2 mod psi squared plus b over 4 mod psi to the 4th, which is a naught over 2 t minus tc mod psi squared plus b over 4 mod psi to the 4th, I can just ask where the minimum of this function is. So I can find the minimum by setting the derivative of the free energy with respect to the modulus of psi to 0. If you don't like differentiating with respect to the modulus, what's wrong with you? This isn't a maths department. So this is fine. And we get a naught times t minus tc times the modulus. Now you see those fractions coming in useful. Plus b times the cube of the modulus is equal to 0. Obviously there is a solution where the order parameter vanishes. That's this point, right? We asked where is the graph flat. The graph is flat at the origin, but clearly that's not the minimum, so we'll just ignore it. So the other solution gives us the minimum, which is mod psi squared equals a naught over b times tc minus t. And so the order parameter is the square root of a naught over b times tc minus t. And so there is a concrete prediction from this theory of how the order parameter grows as we go through Tc, namely that it is a square root. So the theory cannot follow this to very low temperatures because then we would start needing the terms that we've dropped, but it can tell us that near Tc this should come up like a square root, i.e. the order parameter exponent is a half. Sadly, this does not match experiment, but we have some understanding of why it doesn't match experiment. So if only we lived in a 5-dimensional universe, it would match experiment. there's a general sort of thing in these theories that above 4 dimensions, this kind of Landau-Ginzburg treatment becomes basically exact. The exponents all work. In between 4 and 2 dimensions, it's kind of morally right, but the exponents are wrong. Right? Fluctuation effects start to kick in below 4 dimensions and mean that you can't just talk about the order parameter field without fluctuations. The fluctuations become important when the order parameter field is small and they change the exponents. And then below 2 dimensions, you don't develop an ordered phase at all. So by some accident, we are living in the number of spatial dimensions which is right in the middle of the difficult zone. But below 2, no superfluidity. Above 4, mean field superfluidity. But we're in 3, and life is difficult in 3 dimensions, as I'm sure you've noticed. So, nonetheless, we're going to press on with this theory for now. We know it's not getting things quantitatively right, but it does give a very nice qualitative understanding of a lot of the phenomena that we see in the response of superfluids to, various perturbations, various types of boundary, and so on. Okay, so now we're going to start playing around with the boundary conditions and trying to get the superfluid to do something more interesting than just develop a spatially uniform constant order parameter. But as a starting point for that, it's obviously important to work out what form the spatially uniform constant order parameter does take when that's all that happens. Any questions before we start thinking about boundaries?
I have not related to superfluids so much, but can you use Ginzburg-Landau theory to describe relational symmetry breaking? If I add a grad phi 4 term and then I flip the sign of grad phi squared or something like that?
Yeah, like finite Q instabilities and so on. Yeah, sure. Yeah, there's no reason not to do that. But I mean, what that does highlight is that depending on the order you're looking at, the number of terms you have to keep in the gradient expansion or in the potential expansion may be different. And this doesn't tell you from a standing start how many terms you should keep and how many you shouldn't.
It also doesn't tell you that you picked the right order parameter either.
Yeah, that's also true, right? So yeah, indeed. Well, I mean, it just has very little connection to the microscopics, right? This theory does not tell you if a particular Hamiltonian or physical system will actually be a superfluid. It says if it is a superfluid, if there is a superfluid transition, then it should look like this.
So what about B? The temperature?
So the argument is that B will be some smooth, I mean, it will have some temperature dependence, and so will M star. But because the thing that changes sign at the critical temperature is only A, then if we do the Taylor expansion of B around the critical temperature, the leading term will be a constant. So in the spirit of just expanding near TC, we have to keep the linear term in A because we've reasoned that there is no constant term, but there will be a constant term in B and in M star, so the argument is let's just keep those. So we're taking the leading non-zero term of the Taylor expansion in each case. It's just that for A, that's the linear term.
So before we introduced this Ginzburg-Landau, I think it was quite clear where we made the mistake, sort of, because we used the wrong state, not the correct one, or we just used mean field. But now that we changed this Ginzburg-Landau theory, it's not quite clear to me why this is now a mean field description. It just looks like it's any coarse-grained description of an order parameter. So at which point did we make the mistake? Did we choose the wrong order parameter? Or?
What we've done is to focus only on the mean of the order parameter distribution. So even for a classical theory, there will be some distribution of values of the order parameter in space. And we've ignored that when we've said that we're writing the free energy in terms of just this function. So this is the mean of some statistical distribution of order parameter values. And above 4 dimensions, that distribution is narrow enough that approximating it by its mean works out fine. But below 4 dimensions, the fluctuation corrections are important. Good. Other questions? Yeah, please.
You said that the B must be positive because there's no other higher order terms. But maybe there is, so that B is not necessarily positive.
That's right, and if B changes sign, that describes another class of transition.
Yep.
So there are like metamagnetic transitions that happen in magnetic models where B changes sign, but then the C term, the sort of 6th power, is positive. So you can write all of these things down, and they describe different types of transition that we see in nature. So it's not that somehow I have to write B positive. This is more in the spirit of let's do the simplest thing and see if it looks like the transition we're trying to describe. And since it does look like the transition we're trying to describe, we reason that maybe this is okay. But yeah, so that's certainly not a proof. It's a let's do the simplest thing and see what happens kind of argument.
Thank you.
Other questions? Okay, so let's now try and use this Ginzburg-Landau free energy to describe a non-uniform situation, namely when I put the superfluid in a box and I look close to one of the boundaries. Okay, so superfluid near a boundary. So I will place my boundary here at x equals 0, the x coordinate running to the right. So this is the wall of my container, and I want to know what the order parameter does near that wall. So the boundary condition, which feels natural enough, is that the order parameter should vanish at the location of the wall. After all, just to the left of the wall there is no superfluid. If there is no matter, the density is 0, and so the order parameter must be 0. And we assume that the order parameter cannot jump discontinuously between 0 and a finite value, therefore it must continuously vanish as we approach the wall. There's another implicit boundary condition, which I will make explicit. And so this psi naught is the square root of mod A over B. So this is whatever the superfluid would do if the boundary wasn't there at all. So we just proved that in the absence of a boundary, we would just have a constant value of the order parameter, and that constant value is root mod A over B, right? A has to be negative, so hence I'm writing mod A. And it seems physically reasonable that when you are 73 kilometers away from the wall, you don't know that the wall is there, and so the solution you get far from the wall must be the uniform solution that we've already derived. If we have translational invariance in the y and z directions, then we expect our order parameter field to depend only on x. And so this becomes a one-dimensional problem, and the question is, what profile should we choose to minimize the free energy, subject to these conditions? So what profile choose to minimize the free energy, which is now a functional of this function, which tells me what the order parameter is doing. So f minus f naught. Now our spatial integral can be split into two parts. There's an integral in the directions parallel to the boundary, and that's just going to give us the area of the boundary, which is some number, hopefully large. And then we have an integral from 0 to infinity dx. Now the argument will be we can't ignore the gradient terms because we have boundary conditions that won't allow a uniform solution. So this must be h bar squared over 2m star, and then the square modulus, and the only term of the gradient that now exists is the x derivative of the order parameter. So it looks like this. And then we also have, let me write it explicitly as minus mod a over 2 plus b over 4, just to remind us that this term is negative.
By using this formalism, we're saying we want to find out what the superfluid does near a boundary at t near Tc.
Yes.
That's restrictive, right?
Yeah.
We're only doing it because we only have a theory where we can look at it near Tc.
Yeah, that's exactly right. We hope that the qualitative picture will survive because we know there are no further transitions, so the sort of qualitative physics we see near Tc should hold at low temperatures, but the quantitative bits won't work. But of course, since we're below 4 dimensions, the quantitative bits don't work even near Tc, so in some sense maybe we're not losing too much. Okay. Yeah. So, let me, for the sake of argument, assume that the order parameter is real. Notice that when I wrote this, I actually fixed the phase of the order parameter. Right? I could have written this times e to the I phi, but let me just choose a reference in which this is real. So then it's real on the boundary, it's real in the bulk. It seems plausible that it's real everywhere in between. And if we do that, then this becomes a times the integral dx of h bar squared over 2m star, and now this is just, let me just write it as psi prime squared, right, the square of the derivative, minus mod a over 2 psi squared plus b over 4 psi to the 4th, but this is, I'm only allowed to do that because for this particular problem I have good reasons for thinking that I can take the order parameter to be real everywhere. The next trick is a trick but it's a useful one, because to minimize this I'm going to want to differentiate with respect to psi, but I don't have a psi in this term. So that's an awkwardness. I can get a psi in this term by integrating by parts. So instead of, if I regard this as psi prime times this times psi prime, I can integrate that by parts and get minus psi h bar squared over 2m star psi double prime. The boundary vanishes, the boundary term vanishes because at x equals 0, the order parameter itself is 0, and as x goes to infinity, the derivative of the order parameter is 0. So there's no boundary term here, I can just do integration by parts like that. Squared. Okay. So that now is explicitly the free energy for this case, and now we can just manually minimize it. For those who like these things, this is a functional derivative. For those who don't like these things, don't worry about it. It's sort of obvious what the answer is going to be. So differentiating off the psi's inside here, I get minus h bar squared over 2m star times psi double prime minus mod A times psi plus B times psi to the cubed has to vanish. So this is the kind of thing you do when you derive equations of motion from actions, right? You start off saying, I want to extremize the action. Functional derivatives give you Newton's laws. This is very similar, but just for a time-independent problem. Here, we start off with a free energy, which is a functional of the profile, and we say, what equation do we have to solve to get the profile that minimizes this? And that equation is this one. So solve this to get the profile that minimizes f. So it's a bit more work than in the uniform case. It's not just a function, but it's known how to do these problems, and so we just have to look for solutions of this equation that satisfy the appropriate boundary conditions. Any questions? Yeah.
I'm confused about this psi of x real. I mean, so the statement here is that you're fixing the mobile phase of the state wave function, and you're letting the amplitude vary.
Yeah, exactly. And that it's a conjecture that there will be a solution to the problem that has that property, but as we'll show, there is.
But there could be a solution where the phase also varies.
Yeah, and actually when we look at the vortex, we'll see that that kind of solution is necessary there. What we'll show, not to keep you in terrible suspense, is that variations of the complex phase are actually associated with currents. So since in this problem I'm not really expecting any currents, right, the superfluid should just adjust to the presence of the wall and then sit there, then I'm not expecting any spatial variation of the complex phase, which means I can take it to be real everywhere. Good. Any other questions? Okay, so I will not drag you through the solution of that equation, although it is very pretty, but I do want to point out that in the process of solving it, we pull out a characteristic length scale, which is very important for the physics of the superfluid. That's the coherence length or healing length. So really the point of looking at this problem is to introduce that scale. So whenever you try to solve a differential equation in physics, you should try and get the dimensionful bits out of it first by choosing suitable units for everything you're measuring. So there is a set of natural units for the superfluid, which this analysis teaches us. So firstly, I should measure the order parameter as a fraction of its bulk value. Right? So at a given temperature, this theory has a definite prediction about what the bulk order parameter should be, so it's sensible to measure everything in terms of that. So we'll say that my order parameter is psi naught times some function f. So at the boundary, this function is 0, deep in the bulk it's 1. And to remind you, that psi naught is root a over b, so that's what we're doing in terms of the parameters. And the other thing we can do is to note that there's a length scale. And we can work that out by looking at the comparison between these two terms. If these are to have the same dimensions, then A has to have the dimensions of energy, because h bar squared over 2m length squared is an energy. So the units of A are energy units. It follows, therefore, that I can make a length scale out of it by doing h bar over square root of 2m mod A. Right? If this is an energy, then the square root of 2m energy is a momentum. H bar over a momentum is a length. So just by inspecting my free energy, I can see that if A is non-zero, that sets a length scale. This length scale has a name. It's called the coherence length. Or, for reasons that we'll see in a moment, the healing length of the superfluid, and it's a property of that state of matter. You can see that it depends on temperature. A depends on temperature. As we approach the transition, A gets smaller and smaller, so psi gets bigger and bigger. And so this already directly predicts that the coherence length will diverge as Tc is approached. And it even predicts an exponent, because this A goes linearly in T, so this says the coherence length will diverge like 1 over the square root of Tc minus T. That exponent, like all the other exponents in Ginzburg-Landau theory, is wrong, but in 3 dimensions, but at least there's a definite prediction for it.
There speaks a theorist.
Is there any particular reason why we are using M instead of M star?
Oh, the reason is human error. Good, thank you. Any others? Okay, so the rest of it's really just genuine mathematics. So if I take out all of those length scales and condensate scales, I find that, sorry, I didn't actually define the length. So I'm going to measure my length in units of the coherence length. So now I have an equation for f in terms of s, and that looks like d2f by d2s squared plus f over 2 minus f cubed over 2 is equal to 0. And so we're looking for a solution to this that has the property that f, right, so let's restate our boundary conditions. So with f equals 0 at s equals 0, and f goes to 1 as s goes to infinity. And somewhat pleasingly, this equation has an exact solution, which is f equals tanh s over 2. That solution is derivable. You don't have to invent it. The derivation's given in the notes, but I suggest we take this for now. You can check by substitution that it solves this equation. And so our graph for f is just a tanh function. This has the correct boundary conditions. It approaches 1 at large distance from the origin. It emerges linearly from 0 at the origin, and the point at which the rough length scale on which the superfluidity recovers is this s. So if I translate this back into my physical units, that means that the order parameter takes its bulk value in the bulk, obviously, and then deviates from it and goes linearly to 0 at a length scale which is approximately this length psi. And so that justifies the name of psi as the healing length. It's the length scale over which the superfluid can sort of heal back to its bulk behavior if you sort of perturb it in some way, force it to vanish by inserting a boundary or whatever.
And in what sense is it a coherence length? You know,
Yeah, I don't think the term coherence length is very good for this. I think healing length is a much better description because what it really means is the meaning it has in the solution of this problem. That it's the natural length scale over which the superfluid order parameter recovers to its preferred bulk value if something happens to interfere with it. So, yeah, I think coherence length is kind of a bad phrase for it. I don't have a good reason why it should be called that, but it is. Okay, so, yeah.
This is the same mean field theory as the Ising model.
In the Ising model, the order parameter would have been real, but I guess...
we fix it to be real. But like, there it's like a correlation length of fluctuations, right? So
Yeah.
you can also think of it that way.
Yeah, you could think of it that way. Yeah, exactly. But even then, coherence doesn't seem like obviously the right word to use for that. Good. Other questions? Great. Okay, we're going to have time to look at our second example then, which is fantastic. What we've seen so far is that we can write down an ansatz for the free energy as a functional of the order parameter that predicts that far from any boundaries it will take a fixed temperature-dependent value, and it predicts what that temperature-dependent value is, albeit in terms of these unknowns A0 and B. And we've also shown that it can describe situations where I impose a boundary, force the superfluid order parameter to 0, and what it tells us is that it recovers exponentially to its bulk value on a length scale given by this healing length. So that already gives us some useful intuition about how this order parameter behaves. It has a value that it likes to take, and if you disturb it from that value, it will spring back over some length scale which is given by the parameters of the theory. But something we haven't talked about so far, which given that we're allegedly talking about superfluids is perhaps an omission, is superflow. Right? One of the characteristics of the superfluid state is that it carries supercurrents, and we haven't talked about how to write those supercurrents or how to calculate them. So this second example, surely the last of today, is a case where supercurrents come up. So what about currents, i.e. superflow? Now, this is a point where the two-fluid nature starts to become obvious. The point is that there are two distinct ways of running a current in this superfluid. And what I mean by a current is exactly what you think I mean. It is something that transports mass from here to over here. One of those ways we've actually already seen, right? So we know that we have thermal excitations out of the superfluid state, which are these Bogoliubov sound waves. And I could clearly run a current using those. Right? If I have sound waves going one way through the material, that will transport mass. That's a normal current, right? It's happening in the thermal bit that is excited above the superfluid.
does the sound wave clearly transport that?
So if I give it some finite wave vector, then you just have to think about the. Yeah, okay. So if I give it a finite wave vector, it transports mass because it moves the peaks. Right? So if I have a sound wave, I can make a wave packet. If I can make a wave packet, then I can make a wave packet with a group velocity. Now I'm transporting mass. Yeah. So that's sort of anything I could do with any other linearly dispersing wave, I could do with the Bogoliubov sound type excitations, including move stuff around. Have to get the right initial conditions and so on, but you always do. So that's sort of a boring case because it's not really the superfluid transporting matter. It's the stuff you've excited above the superfluid transporting matter. But there is also a different kind of current that you can have here, which does not require the excitation of any of the Bogoliubov sound modes. It's a different way of the system transporting matter, and that comes from spatial variations of the order parameter itself. So that's my sort of first point. What I'm going to write down is distinct from transport by exciting the Bogoliubov sound waves. And the expression for the current, which I'm calling S because it is the supercurrent that we get from variations of this order parameter, is h bar over 2m star I, the conjugate of the order parameter field times its gradient minus the conjugate of that. Since this is something minus its conjugate divided by 2i, I can equivalently say that this is h bar over m star times the imaginary part of psi star grad psi. Now you might ask, how do I know that this expression is the right expression for the current? The answer is that it's the same one you get in single particle quantum mechanics. And the reason that it's appropriate to use that expression here is because this expression for the current actually comes from the existence of the rephasing symmetry of the wave function in quantum mechanics. Right? So there's a symmetry under changing the phase of the single particle wave function, and it follows from that symmetry, via Noether's theorem, that this has to be the expression for the current. There is a symmetry under rephasing of the superfluid order parameter in this theory for the superfluid, which is the same symmetry. And so it follows by Noether's theorem that the expression for the current must be written the same way. So I often find this written down without motivation, and that feels bad, right? Because it feels like we're copying a result from single particle quantum mechanics when we know that we're not doing single particle quantum mechanics. But the point is that this result follows from a particular symmetry of single particle quantum mechanics, which is shared by our theory of the superfluid. And therefore, this is also the expression for the supercurrent here.
So in other words, this is a current because there's some continuity equation that it satisfies.
Precisely. Yeah, it's the spatial component of a 4-vector which would be divergenceless.
And the density which changes is just psi squared.
Exactly. So exactly as in quantum mechanics, it's the square modulus of psi. It's just that we now interpret that as the condensate density, not the probability density for a single particle. Okay. So the origin of the psi is different, but after that, everything is the same. Yeah.
So we don't add or any more excitations. It's just as it was.
Yeah, so obviously in order to get a non-zero value for this current, I'll show in a moment, we have to make the phase of the order parameter wind, which is something it won't do naturally because the free energy doesn't like it. Right? So the gradient term in the free energy punishes all kinds of spatial variation of the order parameter. It doesn't like it if you change the amplitude, and it doesn't like it if you change the phase. So the bulk ground state of the superfluid doesn't have any of these currents. And we'll create them in exactly the same way that we created the amplitude variations in the previous problem, which is to alter the boundary conditions. So if I could arrange boundary conditions where I force the complex phase of the order parameter to be different at the two ends of a wire, for example, then it would have no option but to rotate its complex phase in between, and then that would carry a supercurrent.
So it's a specific case of the ground state.
Yeah, exactly. So this is the point. These supercurrents are adjustments of the ground state in response to changes of the boundary conditions. They are not excitations. You change the problem by changing the boundary. The excitations are the Bogoliubov sound waves, which do also carry mass, but the point is you can carry mass without exciting any of those. It's in the nature of the superfluid state that there are changes you can make to the boundary conditions that force a supercurrent. Yeah.
But in this particular case, because we are at finite temperature, psi has to get also the information, has to have the information within from the normal fluid.
Yeah, of course. So
We're not deriving, so to say, the flow, but some mixture.
no, I completely agree. So that was an aspect which, yeah, I mean, I agree, really. So what I'm sort of appealing to is that the qualitative properties should also be valid at low temperatures. We have this symmetry that gives rise to this expression for the current at any temperature. And so this should still work even when our truncation of the free energy doesn't work. But yes, I agree. If we then start using the Ginzburg-Landau free energy to determine what the phase of the order parameter is actually doing, that calculation would be valid only near TC. This should be more robust because it's only related to the symmetry of the theory. Yeah.
What is the symbol?
Imaginary part.
Oh, this thing.
Part.
Yes. This is a tribute to one of my undergraduate lecturers, Mary O'Brien, who wrote the imaginary part like that. And I always found it very stylish, so I've continued doing it that way. She was really a pleasure, actually, Mary O'Brien. I didn't go to many lectures as an undergraduate because, they were in the morning. But people whose style I liked, I kept going to, and she was great. I particularly remember, it was a course on differential equations, and she turned to us halfway through this discussion of classes of differential equation, and she said, I should emphasize, of course, that everything I've been telling you so far applies to linear phenomena. If one should come across a non-linear phenomenon, I suppose one simply has to throw up one's hands and say, gosh, this is a non-linear phenomenon. Jolly good advice. Good. So let's unpack what this is measuring, because if we rewrite the order parameter in terms of its modulus and its phase, we can see that the current actually is only sensitive to what the phase is doing. So if we write, as we always can, that the spatially dependent order parameter field is some modulus times some phase, that's just a general polar representation of a complex number, then the gradient of this order parameter has two terms. There's the gradient of the modulus times the complex phase. This is the bit that was doing the work in the previous problem with the boundary, right? There was a genuine derivative of the amplitude of the order parameter, but there is also I times the gradient of the phase times the modulus of the order parameter times e to the I theta. And so psi star times the gradient of the order parameter. Right, so when I take, let's just write it out explicitly, so psi star is e to the minus I theta times the modulus of psi. Grad is the expression we just calculated. So that e to the minus I theta is going to cancel these two exponentials here. And so what you get from the first term is mod psi times the gradient of mod psi. And what you get from the second term is I times mod psi squared times the gradient of theta. So that shows you that this expression has two terms. However, this one is manifestly real, and this one is manifestly imaginary. So when I work out the supercurrent, which is the imaginary part of these things, I get only the second term. And so I conclude that the supercurrent at any point in the sample is directly proportional to the gradient of the phase angle at that point. So when people say that supercurrents are phase windings, that this is what they mean. If the complex phase of the order parameter is the same everywhere in the problem, there are no supercurrents. If the complex phase is changing as you go from place to place, then there's a supercurrent in the direction of the change. Obviously, this does also depend on the condensate density. Right? If the order parameter goes to 0, then the phase winding doesn't produce any current. Well, when the order parameter goes to 0, the phase isn't even defined, but the smaller the order parameter amplitude gets, the less current you get per phase winding, which sort of makes sense because you just have fewer particles to carry it. So there's an important consequence of this, which is that if we're in a region of the fluid where the modulus of the order parameter is constant, so in other words, if we have pure phase winding without any amplitude variations, then the curl of the supercurrent is proportional to the curl of grad theta, but the curl of a gradient is identically 0. So what that tells us is that pure superflow is irrotational. And what I mean by that pure is provided it's not accompanied by significant fluctuations of the order parameter amplitude. Which typically it won't be, because there's an energetic cost to making those. So it's typically much more expensive to make the amplitude vary than it is to make the phase vary. And so in most gentle experimental circumstances, the supercurrent is carried just by winding of the phase.
But of course, theta can wind.
Sorry?
Theta can wind. So this
Right, yeah, exactly. So that's what the last observation is going to be, right? Vortices and so on. Any questions about the argument on this board? Yeah.
So at the end of the day, we would always have certain value for the current, even in a time-independent problem, so to say, if I look at the boundaries of this.
Yeah, exactly. So that's one of the things that makes this distinct from the current that you would run with the Bogoliubov excitations, in that because it is dependent only on what you've done with the boundary conditions, it is persistent. Right? There's no time dependence here. There's in a way not even really a sense of anything moving. Right? You've just altered the nature of the ground state by altering the boundary conditions.
And how should we understand this current over the boundaries?
Right, so when you open the boundaries, of course, it becomes a more complicated problem. So the simplest cases where you can think about this are cases where you wrap the superfluid in a ring and then you stir it with something. And you can do this with regular helium. You can also do it with the cold atom gases that people use for these problems. And what you see is that if you set up a state where there is a current going round the ring, that state lasts forever as far as we can measure. And yeah, the reason that lasts forever is because, I mean, effectively by that stirring, you put it into a state that is equivalent to having put a twist in the boundary conditions at the end of the ring. I mean, that's not how you did it, But if you had done that, you would have got the same effect. And so in that sense, it's not, you haven't really put the superfluid into an excited state, you've put it into a state where the boundary conditions have been changed. Now, if you draw the superfluid out, you're effectively changing them back, right? But the details of how you do that is not easy to describe in this language. This is a kind of long wavelength theory. Obviously, when you start drawing superfluid out, you will inevitably make some excitations that change this amplitude as well, and then this neat picture of the superfluid, the supercurrent being proportional only to the gradient of the phase will stop working. So yeah, it's how to connect it to the outside world is a bit tricky, but still, what you see from this is it's a kind of fundamental property of having this kind of order parameter that it sustains this kind of irrotational current. And this is intrinsically a persistent current of some sort. And by the Landau argument, it can't degrade by decaying into sound waves as long as it's not too fast. Other questions about this board? Okay, so I've time to at least pose the problem I wanted to pose as the last piece and sketch the answer. So the worry about superflow being irrotational is that it just seems completely contrary to basic physical expectations. Right? So, for example, I could put my superfluid in a bucket and I could rotate the bucket. Newton thought about this experiment in the context of a discussion, well, not superfluids, but Newton thought about doing this experiment with ordinary fluids in the context of a discussion with Leibniz about whether rotation was absolute or relative. Right? So Newton's argument for why it's absolute is that if I take a stationary bucket with a stationary fluid, the surface is flat. If I then spin the bucket, there'll be a little while when the bucket is spinning and the fluid isn't, and then the surface is flat. Then the bucket will communicate its motion to the fluid, then the fluid will start spinning and the surface will go up, like this sort of centrifugal effect. And then if I stop the bucket, now the bucket is stationary and the fluid is spinning and the surface is deformed, and then the fluid will spin down. And so Newton's argument for why rotation must be absolute is that in the case where the bucket is stationary and the fluid is spinning, the surface is distorted. But when the bucket is spinning and the fluid is stationary, it isn't. So it can't just be about relative rotational velocities, because those two are the same in terms of relative rotational velocities. There must be a real sense in which the fluid is rotating when the surface does this and not when it doesn't. So if I imagine doing that experiment with a superfluid, on the face of it, the irrotational nature of the flow would tell me that since curl of the current is 0, the line integral of the current around any line, any closed contour must be 0 by Stokes' theorem. And so there can be no circulation, and so you just spin the bucket and the fluid just sits there, and it never does this thing that Newton wanted it to do, which is to pick up the rotation from the bucket and curve up. But that seems crazy, right? You're telling me that if I spin a bucket for 7 years, the superfluid in it will never notice and will never start rotating. So our strong intuition is that somehow the superfluid must pick up the rotation from the bucket. But how is that consistent with the argument we've just given that superfluid flow is irrotational? So how can an irrotational fluid ever show rigid body rotation? And the answer turns out to be quite clever, which is that it decides to sacrifice the superfluid state itself in a small fraction of its volume. So the get out is, superfluid flow is genuinely irrotational. If the entire sample remained superfluid, it could indeed never absorb the rotation of the bucket. But at some point, the energetic cost of not absorbing that rotation becomes significantly high. And at that point, it's worth making a little bit of the superfluid normal in order to take up the rotation. So the answer is by making a normal cylinder within the superfluid parallel to the rotation axis. Now you might think that if I only make a narrow normal cylinder, that's presumably not going to be able to take up very much angular momentum. But it turns out that once I have that normal cylinder there, I can have circulation in the superfluid as well. So here's my picture. I've got some rotation axis here, and I make a normal cylinder. So this is the superfluid, this is normal. This happens spontaneously because it's energetically favourable for it to happen. So we've got superfluid all around the cylinder is normal. Care to tell me what the diameter of the cylinder is roughly?
The Healing length?
It must be the healing length. So this is of order the healing length. So I effectively just punch a 0 down through my superfluid, it recovers. But now, if I ask for the circulation of the superflow around this normal cylinder, so I just write a contour and I integrate the superflow around it, I now cannot use Stokes' theorem to say that that circulation is 0, because Stokes' theorem would involve integrating over this whole surface, but the phase isn't defined in the middle now, because I've made this normal. So now I don't have to get 0, but I still have to obey the general formula. So assuming that this is pure superflow, this is h bar over m star, the square modulus of psi times the gradient of the phase angle. If this is pure superflow, this piece is just a constant. And then I get the integral round this circle of the gradient of the phase angle. And that is just the change in the phase angle as I go round the contour. Now, single valuedness requires that this should be an integer multiple of 2 pi. If I come back to the same point, then clearly the order parameter itself must be the same. But for the order parameter to be the same does not require that theta is the same. Theta could have increased continuously as I went round the vortex core, and provided it increases by an integer multiple of 2 pi, the order parameter is still single value. So this is an instance of what we were discussing, a boundary condition which puts some phase winding into the superfluid order parameter.
But this is not related to the phase, but if because of the energy conditions you sacrifice some of the superfluid to become normal and keep rotating, the normal portion would keep increasing, right?
No, because the energy, so you have to think about what the energy is due to the rotating boundary. And this is again one where it's worth changing frames, right? Go into the frame where the boundary is stationary and have the superfluid rotating. And then you pick up a correction to the energy, which is due to the difference in rotational velocity between the boundary and the superfluid. But once the superfluid acquires some circulation by this mechanism, that difference in velocity is not as great. So now there's less of an energetic incentive to put in a second vortex. And so it keeps putting in vortices until eventually the rotational velocity of the fluid matches the boundary, and then there's no incentive to put in any more. So what one can show, I mean, clearly, if this integrated with respect to distance has to be a constant, then the supercurrent of this vortex must go like 1 over the distance from the center. We need a flow velocity that goes like the distance from the center, which is rigid body rotation. And we're going to get that from an area of vortices times a 1 over r circulation for each. So what that predicts is that if I now look down on the top of my rotating sample, it will punch vortex cores in. Turns out they make a lattice, although we haven't proved that. And if I put in a lattice with a constant areal density of these vortices, then all the little 1 over r circulations from each vortex add up to become a total circulation on the boundary which is proportional to the radius. And that's exactly what you have from the boundary itself, right? It's rotating with a constant angular velocity.
Can you repeat this argument? Why did you say J has to go as 1 over R?
So if the integral around the contour has to be a constant, irrespective of the radius of the loop, right, then this length of the contour is going like R, so the superfluid, the supercurrent must go like 1 over R. So that means that each vortex gives you circulation in the superfluid however far you are from it, but it gives you a circulation that goes like 1 over the distance from the core. So if you want to make rigid body rotation, you have to take an extensive number of these vortices, and then the R squared turns the 1 over R into an R. Yeah, please.
So if you rotate a container containing superfluid helium, it would spontaneously generate a vortex lattice at any temperature?
At any temperature.
So even at 0 temperature this would happen?
Yeah.
How would you generate the vortices then?
The vortices in reality spin off from the boundary. So, as usual, spontaneously doesn't mean spontaneously, right? If you had a perfectly smooth boundary, then there would be no matrix elements for creating vortex cores because the boundary could never cause the order parameter to vanish. And so in that case, actually, the counterintuitive result would apply. You could spin the boundary forever and the superfluid would never pick up the motion. But as long as there's any roughness on the boundary, there will be some non-zero matrix element to creating a local zero in the order parameter. Once that local zero forms, there are energetic incentives for it to grow and to swim to the middle of the bucket. So Joe Vinan and Henry Hall are famous for having done this experiment, which is known as the bucket experiment. And you can see the formation of the vortices as you put the superfluid into rotation. Loads. Okay, Andy, go ahead.
Yeah, just a story about that experiment, because I worked with Joe Vinan for a while. You were going to hear, I'm sure, in the superconductivity part about Brian Pippard, who was a very influential guy on the theory of superfluidity and superconductivity. But Pippard had very smart students, and he was a very strident guy. and a lot of real progress came because they suggested something and he said it was nonsense, right? And so this is how that experiment went. Joe Vinan had worked this out, basically, an extremely smart guy, went to Pippard with it. Pippard, derided him. And it happened that for different reasons, Vinan had Henry Hall setting up a rotating cryostat. So Vinan and Hall just got together as two graduate students and said, screw the supervisor, let's have a shot. And look what happened.
Yeah, very nice. So there are now lots of experiments as well doing this with cold atom gases, where in a sense the imaging is easier, but it was done first, obviously, with helium-4. Parasol.
Can you think about this creation of normal fluid in the middle as like a nucleation phenomenon? Because the way that you described it earlier does sound like it.
Yeah, absolutely. So vortices nucleate, and like all nucleation phenomena, something has to kick it off. In the same way that bubbles tend to come from the edge of the glass in champagne, because that's where the roughness is. This is just like that, right? The vortices come in from the edge.
So they form at the edge.
And then they migrate in. Yeah, so I mean, this argument is just that it would be energetically favourable to introduce this lattice. The dynamics of exactly how it gets introduced and on what time scale, this doesn't predict. But the general logic is, in a sufficiently complicated system, there will always be some matrix element for getting from anywhere to anywhere else. So provided that the system is ergodic, it should find this vortex lattice state given enough time.
Why does it need to form a lattice as opposed to one big vortex in the middle?
So one big vortex in the middle would also work. It turns out that this is energetically better. So the energy of the vortex, you can sort of see it here, right? If I double the circulation, then the energy goes like the square of this supercurrent. So doubling the circulation quadruples the energy. So if you want to have twice the circulation, you're better off having two separate vortices of circulation 1 than you are one vortex of circulation 2.
Is spinning here in any way, there's some analogy with magnetic field for superconductors? So
Yeah, precisely. So if I move into the rotating frame, then my Hamiltonian goes to the Hamiltonian minus the rotation across the angular momentum, right? And this looks very much like a Zeeman, an orbital magnetic term. So yeah, in the frame that's rotating with the boundary, the effect of the rotation looks very like an effective magnetic field. Yeah, so the vortex response of superconductors is essentially this phenomenon, with the magnetic field taking the place of the rotation. But we will talk again about superconducting vortices when we get to superconductivity.
Which will be?
So this is more or less all I think it's key to say. So I think let's start superconductivity on Wednesday.
After we've talked about the T's of the fourth.
Okay, yeah, I will make sure I at least know the answer to the question.
Okay.
Any other questions?
We haven't proved here that this is energetically favored. What's the energetics? How to?
Yeah, that's right. So the energetics ultimately come from. You have to think about what the boundary's made of and how the rotation's being done. So what I'm taking as the input to this argument is that it will always be better to have everything in the system rotating at the same angular velocity. I haven't written at a Hamiltonian level where that preference comes from or what the energetic problem is if they're rotating at different bits. I've just assumed that if you have a system of two rotating parts, the energy associated with the relative rotation goes like the square of the difference between the rotation speeds. And so then I've argued that to reduce that, you want to make the rotation speed of the superfluid match the speed of the container. But yeah, that's certainly a hand-waving argument. I just wanted to point out that the irrotationality of the superflow doesn't stop it from doing bulk rotation. It just finds a clever way of getting round this Stokes theorem restriction.
So would you always get this kind of vortex lattice no matter how fast it rotates, or does it somehow depend on like the amount of vortices, for example?
So the circulation is quantized. Right? So I cannot make circulation less than one vortex, but I can rotate my boundary slower than one vortex would be needed, right? So actually what happens is that up to a certain rotation speed, the equilibrium state is still 0 vortices, right? So it will tolerate that mismatch in rotation up to a point because it has no option. But as soon as it becomes better to have one vortex than 0, right? So when the circulation of the boundary passes the sort of pi level, then it will pop a vortex in, and then that one vortex will persist for a while, and then you cross 3 pi, and it becomes better to have 2 than 1. So it's actually a staircase thing, right? The number of vortices as a function of the rotational angular momentum is actually strangely hypnotic. Actually looks like that. So there's actually a staircase of critical rotation velocities where it becomes worth putting another vortex in, and the system jumps at those rotational velocities ideally between a 0 vortex ground state and a 1 vortex ground state and a 2 and so on. And this is observed, right? You can change the rotational speed, you can see when the vortices go in, and it matches this prediction.
Writing flux quanta through a Josephson junction or something.
Which of course we'll discuss when we get to superconductivity.
But I think the question was more whether there's some sort of critical velocity in the same way that we had for, unidirectional flow, and where it stops being superfluid.
Sure. Okay. Sorry. If that was the question, then yes, of course there will be, because this 1 over r circulation is a 1 over r superfluid velocity. So at some point, the superfluid velocity at the edge of the vortex is going to exceed the superfluid critical velocity, and then the normal regions will grow. So yeah, there's the same instability there. So if you spin a superfluid too fast, the whole thing will go normal. And it effectively goes normal by the merging of the vortices.
There would be a question. So it's really the lattice is getting too dense and they start merging.
Yeah, exactly.
The lattice spacing?
So it spreads these uniformly over the vessel. So the lattice spacing is determined by the number of vortices that you want. So this lattice spacing, AL, is basically the square root of the number of vortices divided by other way around. Inverse. Yeah, so it's the square root of the area divided by the number of vortices. You know the number of vortices you need because you need the right number to get the correct angular velocity to match the rotation of the boundary. So that tells you the number of vortices, and then they just spread approximately evenly across the area. So as you crank up the rotation, more of them nucleate from the outside, and the inner ones move in. And so it's like you're zooming out on a vortex lattice that was always there in a way.
But what's the critical, is the critical density just going to be on the order of the healing length, or will it be before you get to that density?
I think it will, although, and I think in the Bogoliubov, the weakly interacting theory, because I think a sort of conspiracy of these length scales means that the density at which the vortices materially overlap is the same as the density at which the circulation at the boundary becomes. Yeah. So no, this is fine. So the collapse must happen by vortex overlap because each vortex is not changing its circulation. So it's not like as I spin the boundary faster and faster, each vortex is spinning faster and faster. So if the vortex was allowed to exist at low rates of rotation, it's allowed to exist at high rates of rotation. It's just that the vortices get close enough that the cores start overlapping, and then the superfluidity collapses. Good. We should probably think about lunch, to whatever extent we're not doing so already. But thank you everyone as ever. The video will go up this afternoon. I'll upload the notes as soon as I can. And on Wednesday, we will come back to the T to the 4th.
Which might be a strong coupling.
Yeah, indeed it may. And then we will start talking about what happens if this superfluid becomes charged.